Hi everyone, I'm Atsuki from Nagoya University and Second. Today I'd like to talk about our recent work on communication complexity, the Byzantine Agreement, which is a building block of many distributed cryptographic protocols. This is a joint work with Lin from UIUC. Byzantine Agreement is a consensus problem in a network of parties, where a set of n parties have their own input values and agree on a single output value in the presence of at most f faulty parties who can behave arbitrarily, which is called Byzantine fault. Honest parties don't output different values, and every honest party eventually outputs a value. These are called consistency and termination. And the validity requires that if every honest party has the same input value, every honest party outputs the value. So this is also called unanimity. For Byzantine agreement, there are two well-established models. The first one is the unauthenticated model. In this model, we cannot use any cryptography, and the protocol achieves information theoretic security. And in this setting, n-third is the best possible fault tolerance. On the other side, the authenticated setting means we can use some cryptography, such as digital signature with a public infrastructure. Digital signature allows parties to sign messages to show and verify that the signed messages came from the signing parties. In this setting, Byzantine agreement is possible for up to n-half faults. In Byzantine agreement, communication complexity is an important efficiency metric because communication cost is often a bottleneck in its applications. The communication complexity of a protocol is the maximum amount of bits transferred by all honest parties combined across all executions. So this is a worst-case communication cost of the protocol. Let me give you some examples to help you understand intuitively. If all parties can multicast, which means all-to-all communication is possible, it costs quadratic communication. And if the message contains a linear messages, for example, a set of votes from a quorum of other parties, it will cost cubic communication. For Byzantine agreement, it is well known that quadratic communication is necessary due to the lower bound shown by Donovan ratio. Berman et al. Showed that this lower bound is tight for the authenticated setting with the best possible fault tolerance of n-third. However, in the authenticated setting, the best solution has been the famous Doliff-Strong protocol with cubic communication, so a linear gap remains for this case. In this work, we present two results that help close the remaining gap. Both results achieve the optimal quadratic communication, but have trade-offs in fault tolerance assumptions. The first result achieves the optimal fault tolerance, but assumes threshold signatures. So we need a trusted key setup. Please note that quadratic bound holds even after assuming ideal threshold signature. The second result achieves the nearly optimal fault tolerance of half minus epsilon n for any positive constant epsilon, but it only assumes PKI for digital signatures. Before moving on to the details of the protocol, let us clarify the other assumptions. We assume the lockstep synchrony model, where every party runs at the same clock speed called round, and all messages sent by honest parties are delivered by the next round. Our protocol tolerates an adaptive adversary that can corrupt parties anytime in the protocol execution. In the rest of this presentation, we explain our protocol in 2 steps. To achieve the quadratic communication complexity, we first revisited the Berman et al.'s protocol and abstracted it to make it independent of the fault tolerance. And this gave us an important observation that the Berman et al. Protocol has a problem reduction framework from Byzantine agreement to a well-known problem called graded agreement. And the Berman et al. Protocol tolerates only n-third faults because the graded agreement in the Berman et al.'s protocol tolerates only n-third. So we first explain how the Berman et al.'s protocol achieves Byzantine agreement from graded agreement. And then we solve the graded agreement problem for more than n-third faults in 2 ways, which result in our 2 Byzantine agreement protocols. So we first explain how to achieve Byzantine agreement from graded agreement. The Berman et al.'s protocol is a recursive algorithm. It partitions the set of parties into 2 hops and run the BA protocol recursively until the partition becomes sufficiently small. Because a whole set of parties has at most 1/3 fraction of faulty parties, the fault fraction is preserved in at least one of 2 hops, and therefore one of 2 recursive BA calls must be correct. But of course, the other one might be incorrect. So the challenge here is how to follow the result of the correct one to make the caller correct. In the Berman et al.'s protocol, this is achieved by running a hand-tailored preprocess called Universal Exchange Protocol prior to the recursive BA calls. However, it doesn't work with more than n-third faults. Our key observation in this work is that the universal exchange process can be abstracted as a well-known problem called graded agreement. Graded agreement is an agreement problem similar to Byzantine agreement, where each party has its own input value and output value and a grade bit called G. If an honest party outputs the value with grade 1, every honest party at least outputs the value. But it's okay, the grade is either 0 or 1. But if every honest party has the same input value, every honest party outputs the value with grade 1. And every honest party eventually outputs a pair. This problem is significantly easier than Byzantine agreement because it requires an agreement on a single decision only when someone outputs grade 1. So if no one outputs grade 1, parties can even output different values. In each recursive BA call, the input of the BA is input to the graded agreement in the first step. And the graded agreement determines the input of the BA in the partition 1. If the graded agreement outputs a value with grade 1, follows a graded agreement and ignore the Byzantine agreement. And otherwise, follows a Byzantine agreement. In the same manner, in the second step, run the graded agreement, which determines the input of the Byzantine agreement in the partition 2. If grade 1 follows the GA, and otherwise follows the BA. And the result of the second step is the final output. There are 2 key ideas behind this construction. The first idea is that if all honest parties already agree on a value at the beginning of each step, they all output the value at the end of this step. This is because if everyone input the same value to the graded agreement, everyone output the value with grade 1 and follows the result of graded agreement. So even if the Byzantine agreement is incorrect, it cannot affect the final output of this step. And the validity of the Byzantine agreement protocol is straightforward from this idea. If all honest parties input the same value, which means they already agree on a value from the beginning, everyone output the value in step 1, input the value to step 2, and output the value in step 2. So both step 1 and 2 don't change the agreed upon value, and all honest parties output the value. The second idea is that all honest parties agree on a value at the end of the correct step. There are two cases to consider to explain this idea. The first case is when someone outputs the value with grade 1 in the graded argument. In this case, everyone at least output the value with either grade 0 or 1 and input the value to the Byzantine argument. Because the Byzantine argument in this step is correct, everyone output the value in the Byzantine argument. So all honest parties, whether their graded argument output grade 1 or not, agree on a value at the end of this step. The second case is when no one outputs a value with grade 1. In this case, everyone follows the correct BA's result. So in either case, all honest parties agree on a value at the end of this and the correct step. These two ideas help achieve consistency. If step 1 is correct, everyone agrees on a value at the end of the first step. And the step 2 don't change the agreed upon value, even if step 2 is incorrect. So the final output must be consistent. And if step 2 is correct, step 2 drives consensus on a single value, even if honest parties output different value in possibly incorrect step 1. Now, it's very easy to see that if the graded argument protocol costs at most quadratic communication, the total communication cost of the Byzantine argument is also quadratic. Please refer to our paper for the details of the analysis. So the remaining challenge is how to solve graded argument with quadratic communication for more than n-third faults. First, let me give you a simple Warmup protocol. The protocol has 4 multicast rounds. In round 1, each party sends its input value to all other parties as both 1. And then in round 2, if a party receives a majority vote 1 on a value, forward it. And then in round 3, if the party doesn't receive majority vote 1 on another value, follows the majority vote and send vote 2 on the value, vote again. And in round 4, if a party receives majority vote 2 on a value, forward it. And if a party receives majority vote 2 on a value, output the value. And if it receives it in round 3, the grade is 1. And if it is in round 4, the grade is 0. Here, as in most Byzantine fault-tolerant protocols, what these 4 rounds achieve is that majority vote 2 cannot be collected for 2 different values. This is due to forwarding majority vote 1 in round 2 that allows eliminating conflicting vote 2 between honest parties in round 3. Then, after eliminating conflicting vote majority vote 2, it's very easy to achieve consistency. This is because if someone outputs the value with grade 1, the party forward the majority vote 2 in round 4. So everyone receives the majority vote 2 by the end of round 4 and output the value. But unfortunately, this strawman protocol requires cubic communication because everyone forwards a linear size majority vote 1 in round 2. We solve this problem in 2 ways. And this is a key challenge of this work. The first and the easiest solution is the well-established use of threshold signatures. Before forwarding majority vote 1, the party combined the set of n minus f vote 1 into a single signature using T of n threshold signature with a threshold of T equal n minus f, the quorum threshold. T of n threshold signature allows the party to combine a set of signature shares from T different parties into a single signature with the same length as an individual signature. So forwarding majority vote 1 in the form of a combined signature causes quadratic communication. But because all existing threshold signatures require trusted threshold key setup, the assumption is very strong. In order to eliminate the trusted key setup, our second solution introduces a new technique that uses an expander. Expander is a graph of nodes with good connectivity. An alpha beta expander is a graph of n nodes where any subset of alpha n nodes has neighbors of more than beta n nodes. And it is well known that for any alpha beta, a constant degree and alpha beta expander exists. In our protocol, we will use n 2 epsilon 1 minus 2 epsilon expander with constant degree. In our protocol, in round 1, everyone votes on the input value as before. But in round 2, parties don't forward a majority vote 1 to all other parties. Instead, each party forwarded only to the neighbors in the expander. And then in round 3, if the party doesn't receive majority vote 1 on another value, follows the majority vote and send vote 2 on the value to all other parties. Here, because the expander graph has constant degree, the total number of communication links is linear. So even if parties forward linear sized messages, the total communication is kept quadratic. Finally, let me explain how the good connectivity of expander is enough to eliminate conflicting majority vote 2. Suppose a majority vote 2 is collected for a value. Then at least n minus f, which is at least f plus 2 epsilon n parties. Out of these, at least 2 epsilon n honest parties must have sent vote 2 on the value. So they must have forwarded the corresponding majority vote 1 to the neighbors in the expander graph. Then, due to the expansion property, at least 1 minus epsilon n, which is more than 2f parties, out of which more than f honest parties must have received the majority vote 1. So the honest parties could not have sent vote 2 on different values. So n minus f vote 2 on a different value cannot be collected. And we can eliminate conflicting majority vote 2. As a summary, the solution 1 achieves the optimal fault tolerance, but requires a strong trusted key setup for threshold signature. And the solution 2 requires only PKI for digital signatures, but the fault tolerance is nearly optimal due to the dependency on the parameter of the expander graph. And finally, plugging the 2 graded argument protocols into the Berman et al. Recursive framework achieves the optimal quadratic communication protocol for Byzantine Agreement with 2 different assumptions. Thank you very much.